Okay, so we continue with the analysis of numerical schemes in this class, and we're going to discuss a lot about numerical diffusion. I hope to cover that today, and we will discuss the last 4 steps to the Navier-Stokes next class. So this is where we left off last class. We did this derivation discussing the modified differential equation. If you recall, if you have your notes nearby, you will recall that we were using again the linear convection equation in one dimension, and we discretized in the following way. We had, as you can see here, a forward difference in time. This is from last class, and we used a central difference. You see here the central difference in space, taking 1 point from each side. So what we did is we looked at this discretized equation, and we took each one of these terms that is not the central one, u and I, and we wrote a Taylor expansion for that. So we have a Taylor expansion for un plus 1i, another one for un I plus 1, un I minus 1, and we have them right here. We did these Taylor expansions. Then I say, well, I can rearrange some terms so that I can get these expressions that appear in my discretized equation from the Taylor expansions for all terms except the uin. So I subtract this, subtract let me see, let me change color to 3. Subtract this guy to the other side, divide by delta t, and I've got the first term, you can see. Subtract un minus 1, subtract un I from both sides here, subtract here, divide by delta x, and I subtract these two, and I can get this term here with my delta x. And when I subtract, I get 2 delta x and the first du dx, and this guy du dt appears. Oh, well, I've divided by delta x, so I only have, you can see that these guys appear as well from my rearranging terms, right? So that's where I get these from here. Let me change color here. This one gives me that after divided by delta t. These two give me that after divided by delta x and multiplying by c, so that I could get those equations. Everybody follow? Okay. So you can see that there are other terms left over in all of these equations which appear here, which constitute what we call the truncation error. And this is where we were last class. So we pick up from here. You notice that the truncation error then is the difference between the numerical scheme, this guy, the numerical scheme, and the numerical scheme is here, and the differential equation. The difference between the numerical scheme and the differential equation. In the example we just did, the truncation error, of course, you could see that it vanishes when delta t and delta x go to 0. So this indicates that the scheme is consistent. The truncation errors must go to 0 when your steps in time and space go to 0. Consistency. And the thing to note, the thing to note here is that the exact solution of the numerical scheme not the differential equation, satisfies a modified differential equation. We call it modified, some people call it equivalent differential equation. Which of course differs from the differential equation by the truncation error. So let's consider the exact solution, of the discretized equation And we're going to call the exact solution of the discretized equation u bar n I. So of course, if this is the exact solution of the discretized equation, then it satisfies exactly u bar n plus 1 I minus u bar n I over delta t plus c over 2 delta x un bar I plus 1 minus u n bar I minus 1. So this is identically 0 because it's the exact solution of the numerical scheme. So from the previous equation where we had the numerical scheme, the differential equation, and the truncation errors, okay, if we put in the exact solution of the numerical scheme in there, the first terms, of course, are going to be 0, right? The first terms are the numerical scheme, so those, let me just go back. It's going to mess up the slide so you can see it. Anyway, this guy over here I'm talking about, this is the equation, okay? I'm going to put it in this equation here. I'm going to put u bar in this equation. This is going to be identically 0, so I'm going to be left with this and the truncation error. You agree? Okay, so I'm going back forward now. So, from, what did I call it? An asterisk, right? We have the first few terms of 0, and I only have these differential terms, du bar dt plus c du bar dx, and these are now evaluated at n and I. And on the right hand side I had all the truncation error terms. So minus delta t over 2, second derivative of u bar now with respect to time, n I minus c delta x squared over 6, and the third derivative of u bar, and also n and I, plus these terms which are, or minus, doesn't matter really, order delta t squared and delta x to the 4th. Okay, so now let's, to write less, I'm going to use subscript t to indicate du dt, and subscript x to indicate du dx, okay? So I can write a little bit less. And so I'm going to write now, from this equation, just to the lowest order. So I'm going to take just this equation, but to the lowest order. So I'm going to just cram these things into one big O notation. We call this big O notation. And I'm going to write u bar t, that's the derivative with respect to time, n I. I'm going to move this guy to the other side, equal to minus c u bar x, that's the derivative with respect to x, n I. And I'm just going to put all of these other terms together in a big O notation, order delta t and delta x squared. So now I'm going to take an additional time derivative, so d dt of the equation above, and I'm going to get u bar t t. You can see why I didn't want to write the partials anymore. And I equals minus c, I changed color so you can follow the line better, u bar x t, the mixed derivative, and I plus the order delta t delta x. They don't disappear because they're not constant terms. They're terms that have derivatives and so on. So there's going to be some derivatives multiplying these terms. They don't disappear, but they also don't change order, right? Okay, so I'm going to switch around these. I assume that these, of course, are smooth enough so that I can switch the order of integration. So I'm going to write it like this. U bar t, then I take the derivative with respect to x, and I plus order delta t, delta x squared. So in here, now I use this guy. You can see I have ut in there, so I can use this guy, right? And so I have finally that u bar t t n I is equal to minus c, and I have, so notice I'm taking a derivative with respect to x of this term, so I have double derivative with respect to x. The minus c stays there, but I have well, actually I have two c's. I have this c over here and the c from this guy. So I have, the minus goes away, and I have c squared. Okay, good. So we have c squared, and we have the second derivative with respect to x when I put this guy in there. And we have terms of order t and x squared and terms of order t and x squared, which we just grouped together. So plus order delta t and delta x squared. Are we good there? Okay, so I have an expression for the second order derivative now that we're going to put back on the truncation error. In the truncation error, the first slide that I showed in the beginning, we had the numerical scheme minus the differential equation equals the truncation error. That truncation error, the first term had delta t over 2 and the second derivative of u with respect to time. So we're going to put that in there. Okay? Okay. So we put back in, I think I called it asterisk, and we get that the truncation error, I called it epsilon t, is equal to, so this is the term I'm replacing now. So here's my c squared, and I had a delta t over 2 from the truncation error expression, and now I've been able to replace that second order time derivative by a second order space derivative. And so I have all space derivatives because the other term had delta x squared over 6 and ux triple x here, plus order delta t squared and order delta x fourth. Therefore, the exact solution, I think, yeah, I got all my bars there over the u's. The exact solution to the numerical scheme which we've called u bar, satisfy the following differential equation. U bar t plus c u bar x equals to u bar xx plus order delta t squared delta x fourth. Okay. So this is the modified differential equation.
What happened to the u triple x term?
Ah, okay. Delta x squared. That's why I have delta x squared. Thank you. So that's why I've written here delta x squared. I've put it in there. So all the second order terms are bolstering together there. Thank you, Victor. This is what we call the modified differential equation. The equation satisfied by the exact solution to the numerical scheme. So, what do you observe in that equation? What can you tell me about that equation? You know, Jeremy. It's somewhere like that. It's like our convection diffusion equation. It's not a convection equation. It's actually a convection diffusion equation because we have a term here that looks like the diffusion term, right? So this is the interesting stuff. We have, this is not a convection equation. It is a convection diffusion equation. So, it's a convection diffusion equation with a numerical diffusion. This is a numerical diffusion. It depends on delta t over here. We call this a numerical diffusion. Coefficient equal to, actually I'm going to use the red for this one because it's important, minus c squared delta t over 2. So, what can you tell me about that diffusion coefficient? There's something not nice about it. Very good. It's negative. Negative diffusion. What is a negative diffusion? We discussed it in the beginning when we were discussing all our mathematical models, right? Our model equations. Negative diffusion is a process of explosion, which explains why the scheme is unstable. This shows why the scheme is unstable. A physical process of diffusion with a negative viscosity will amplify exponentially any disturbance. It's like an explosion. Okay? So the modified differential equation and the truncation error provide essential information about the scheme. All right? So now let's look at, we have already done it, but let's kind of just summarize the method for obtaining the differential the modified differential equation. So we are going to denote by capital D of U the actual mathematical model, the differential operator applied to our solution U equal to 0. That's our mathematical model, a differential equation. and we also denote by n of u, but at a certain grid point, the numerical scheme. So what is going to be our method for obtaining the differential equation? Well, first we do the same that we've done before in the beginning, in the end of the last class and the beginning of this class, which is to perform the consistency analysis. By obtaining the truncation error, using this, basically using the Taylor series expansions and obtaining the truncation error. Epsilon t. In an equation similar to the one we had in the beginning of the class. So we are going to get something of the form n, the numerical scheme applied to u, n I, minus d u equal to the truncation error. This is, in short, what we had in the beginning. So that's the first step. The second step is to consider the exact solution of the numerical scheme, like we also just did. And, of course, for the exact solution of the numerical scheme, u bar and I, we have, it's defined by, it's by definition, n, u bar and I, exactly equal to 0. And this is going to lead to the differential equation D, the differential operator applied to u bar and I, the exact solution of the numerical scheme, equal to minus the truncation error. I'm going to use a bar there now because it's the truncation error basically evaluated at u bar. And then the third step is going to be to replace the lowest time derivative by a space derivative, like we also just did. That is, we do that in the expression for the truncation error by applying the differential equation in step 2. By applying the differential equation of step 2, which is that one over here. And the final step, step 4, the modified differential equation is defined as an equation obtained after the replacement step 3 restricted to the lowest order terms. Containing now that contains only space derivatives, okay? Like we've just done. So let's do another example. So this also you have seen before. That's our step 1, I think. And we're going to now introduce the Taylor expansions that we wrote before. I'm going to skip some steps because it's too much writing. You can try to reproduce this if you want in your own time, but you will probably see them right away. So we introduce the Taylor expansions as before. As before, and follow steps just listed, and I'm going to write the final answer, which is du, well, not the final, but an intermediate answer that we need, du dx. So this is now the differential equation, but applied to the exact solution of the numerical scheme. C du, sorry, this is the time here. And that's equal to C delta x over, do we have a 2? Yes, we do have a 2 in this case. 1 minus C delta t over delta x, and the second derivative of u bar with respect to x. So basically we're only using the first Taylor expansion for time. You can see how that one will generate the a similar expression that we have as we had before. We've done all the steps here. Okay, so I've just skipped all the steps here and given you the modified differential equation all the way to the end. So this is the modified differential equation for this case. I wanted to skip some steps where this guy here, you can see again that it is not a convection equation, it's a convection diffusion equation, and this guy here is the numerical diffusion. So again, the numerical solution obeys a convection diffusion equation. So the numerical diffusion term, which is right here, has to be positive for disturbances to be damped in time. So what we want is that, well, of course, if this expression here was negative, then the solutions would explode. Basically, any disturbances will grow in time, like we had in the previous case, and it would be unstable. But for stability, we're going to require then, for stability of the first order upwind scheme, which we use for step 1 of the assignment, we need that 0, we need this to be greater than 0. C has to be greater than 0, so that this is all positive, and this also has to be positive so that C delta t over delta x is smaller than 1. So we have the two conditions. We have C greater than 0, and this parameter is called, let's call it sigma, equals to C delta t over delta x. This has to be less than 1. Sigma is called the CFL number. CFL for Courant, Friedrichs, and Levy. These guys observed the stability condition for this numerical scheme. This is the CFL number, and basically this CFL condition, as it's known, is CFL number less than 1, which already Brian discussed in his presentation briefly without giving it a name. Now this is actually has tremendous important physical significance and also significance in terms of the numerical approaches, and we're going to discuss a lot about this today. But it also has significance in terms of the physics. We'll discuss more about this later. And for a constant value of sigma less than 1, then you can also see that the scheme has a numerical diffusion which is of order delta x, which is generally excessive. Basically, we're saying that this scheme has poor accuracy. It is stable, but it has poor accuracy. Does that answer a lot of your questions from the first part of the assignment? So now, if you go back, now I would suggest that you play around with your codes that you've already created, and they're ready to all you have to do is change around the numbers, and perhaps you want to change a little bit your input so that now it's always, perhaps you want to force it to always be stable or something like that, but you could play around with it at this point, the way that you have written it, with different values of delta t and delta x, and confirm that in fact you need to respect this relationship.